Okay, so in the second part of the course today, we look into camera calibration, but now in using a known 2D pattern. So assume you have a plane. On this plane, you have this checkerboard pattern, so just black and white squares. Why checkerboard? Because you can very easily identify those points. You have a large number of those points. They all lie on a plane. And we typically can assume to know the size of this checkerboard. So we know the size of the whole checkerboard, and therefore also the locations of those points on that plane. So it's just a 2D pattern, could also be a different pattern, but often one uses such checkerboard patterns because they're really easy to use. But the key thing is we have a known 2D structure, a 2D pattern, and we know its size and its structure. And we can identify points on this plane, and then we know where those points on the plane are in reality.
Theoretically, you could have also used the shirt of the guy who's holding the checkerboard.
Yes, but what we actually will do is we will explore. So the question was if we could also use the shirt of the guy holding the checkerboard. We can't, because we will make an assumption that the points lie all on a plane. And this is not a plane. Or typically not. But otherwise, that would be possible. So if the guy would have a perfect square body and the t-shirt would fit very well, maybe, but in this case, I think it's better to rely on that checkerboard. Okay, so what we can do is we can identify all those points in here. And we can now use a certain trick. We say, okay, I know where those points are on the plane. If I set my world coordinate frame in a smart way, I can ensure that I know the world coordinate of all those intersections here. How can I do that? Which trick can I apply to for every image, apply to this image an own reference system, an own world reference frame or object reference frame, so that I know the location of all points in the world? Any idea? So I know where those points are on the checkerboard because the checkerboard has a known size and structure. What I can do now is, okay, so let's simply use this point over here, and that's our reference frame, so that this is the x and y direction, and that is orthogonal to the plane. Then I know that the z coordinate of all points is 0, and the xy coordinate depends on the point on the checkerboard. And I know the checkerboard, I know the 2D pattern. So what I do is identify those points, take one of those points, say, okay, that's my coordinate system, and then I know they all have a z coordinate which is equal to 0. And given I know the size of the checkerboard, I can also compute actually their xy location on the checkerboard. It's kind of just a very simple trick of taking a 2D pattern and saying, okay, for every image of the checkerboard gets an own world reference system, and simply the checkerboard defines the reference system, or the coordinate system, the reference frame. Okay? Let's see how this simplifies our math. I wouldn't do that if it wouldn't simplify our math. Okay, again, my calibration matrix K, my matrix containing the extrinsic parameters, the point in the real world on the checkerboard, and where this pixel is generated in the image. So what
Now all points are on one plane.
Yes, all points are on one plane. This is something where the DLT would fail. But we now put them explicitly on the plane, and we'll now see how we can exploit that fact. So we said the z coordinates of all points are 0, because that's how we defined our reference frame. So this guy is 0 for all points. So let's exploit that, because this element is multiplied with this vector. So all those elements, or if I multiply, this vector with this vector, this vector with this vector, and this vector with this vector, those are the elements which will be multiplied with z equals 0. So they will simply be eliminated. So they don't matter. Whatever values they take, they don't matter. You can say, okay, perfect. Let's simply delete that. Simply delete this column over here. And then our matrix simplifies. Oops. The Z is gone over here, the third column is gone over here. And now I say, okay, I'm still in homogeneous coordinates. I have something in 2D here. I have a transformation which is linear. And I have 2D over here. So perfect. What I actually have is I have homography in the projective space of 2 dimensions, P2. All this weird projection is gone. This 3x4 matrix is now gone by just setting the coordinate system in a smart way. So when I have this matrix over here, it's an homogeneous matrix. So how many degrees of freedom does this matrix have? Why 9? Perfect, 8. So 9 is the intuitive choice because it's a 3x3 matrix for 9 elements, but it's an homogeneous matrix, so I have this scaling factor, this one over here, so it boils down to just having 8 degrees of freedom. Okay. So let's have a closer look to those elements in here. I can describe this as my matrix K, my calibration matrix, and a matrix which now contains 2 columns of my rotation matrix and my translation vector T, because the third column was eliminated. I can actually write this in this way. So I can actually write the system exactly in this way. So I have my 2 image coordinates. I have the 3 column vectors of the homography, which is just those 2 guys multiplied with each other, corresponds to the XY1. I get that for one single image like this. For one single point like this. But I can do this for every point on my checkerboard. So if I do this for all my points on my checkerboard, I simply have this system over here and for I different points on my checkerboard. And I want to estimate this homography over here. How do I do that? How do I proceed? We have a matrix over here. We have some points over here which we measure. And we have some points over here which I know. Which are my control points on the checkerboard. If you press a rewind key in your brain and go back for 30 minutes maybe, we had exactly the same problem in the DLT. The only difference was that we had 1 vector more in here. Right? Just more unknowns. P had 12 elements, and this matrix has 9 elements. But who cares? We just go analogously to step 2 and 3, or 1, 2, and 3 of computing the DLT. So what we have in the end, okay, instead of estimating a 3x4 projection matrix, we estimate a 3x3 homography, and the rest is identical. Just everywhere where that coordinate is, the Z coordinate can go away because we don't have Z anymore. And we don't have the third column of my rotation matrix anymore. So I can again define my weird vector A. I don't multiply it with P, just with H, because H is now the stacked vector. And so it's exactly defined in the same way, except I had P here before. And okay, now you know where the cross is coming from. There are a few elements in this vectors A which are not relevant anymore. Those which correspond to the Z coordinate, they simply die. And the rest stays the same. We again have this, we set up our matrix M, we compute the SVD, and here we are. Oops. So we have exactly the same thing before, just kind of the same slide as before, just these vectors A are kind of shrunk now, where I crossed out the coordinate. So I do exactly the same what I did before. I do a DLT-like estimation, except that my vector P is now smaller, 3 unknowns less. Only have 9 instead of 12. But the rest basically stays the same. So what we get if we do that, we solve the system of linear equation by minimizing the squared error using the SVD and obtain our solution. We have 8 degrees of freedom that we have in there, so we identified correctly, taking account the normalization appropriately into account. As before, we measure 2D locations of points in my image, so I get 2 equations per point. So I need at least 4 points on the checkerboard in order to estimate this homography. Okay? So at least 4 points are needed in order to do that. Typically it's like that. In this case, we have defined our coordinate system. So 6 degrees of freedom go into the coordinate systems. So 2 degrees of freedom are left that contribute to my calibration matrix. So we'll need actually, in the end, as we will see, we will need multiple images in order to estimate all the intrinsic parameters. Okay, oops. Okay, let's go back and say, okay, what you now need to do is we need to compute from matrix H. So we computed H. We want to estimate all the individual parameters. One of the things is we can't do the trick with the QR decomposition now because this matrix is not a rotation matrix anymore. So we can't just apply the QR decomposition as we did before. This simply doesn't work in here because this is not a rotation matrix anymore. So this is now a bit more tricky now. So we need a little bit, invest more brain power into this part. What we need to do is now we will define some constraints, some of the things we know about this matrix in order to set up a new system of linear equations, solve that in order to estimate those parameters right. Okay, so we start at this point. We know all the elements in H. So H1, H2, H3 are known. That's what I got from the previous step, from the DLT-like estimation. And now my next steps is turning that into my matrix K, which I actually want to have, and maybe also the extrinsic parameters, or parts of them. Fine so far? Everyone knows what to do? Good. Okay, so what we do now is, as I said, we generate now certain constraints we know about those elements, especially those elements which sit in here, to exploit those constraints in order to estimate the calibration, our matrix K, so the intrinsics, matrix of the intrinsics. So what do we know? The first thing we know is, given we apply this, how are R and H related? Saying simply R1, so this one, is k to the power of minus 1 times H1. Just get that if I multiply from the left-hand side with k to the power of minus 1. So this matrix goes away, if k to the power of minus 1 H1. I can do the same thing for R2 and H2. So it's clear how I obtain those equations? Just by multiplying this line with k to the power of minus 1 from the left. Okay, so what do I know about R1 and R2? Where do R1 and R2 come from? Where do they come from? What are those values?
So they come from a rotation matrix. So
Yes.
they are in between 0 and 1.
Yeah. So these are the elements of the rotation matrix. So what do we know about if we take two columns out of a rotation matrix? What do we know about those two vectors?
The axis they rotate around.
Yeah, they're nearly there. So I have rotation matrix, take out two of the columns of the rotation matrix. What do I know about this rotation matrix? About those two vectors? They are orthogonal, right. The first constraint, they are orthogonal. What's the second thing I know about their length? Length 1. There are two constraints I want to now exploit. So R1 times R2, so dot product R2, should be 0 because they are orthogonal. And the norm of those two should be 1. Okay, so these are exactly my two constraints. that I want to exploit now. Let's exploit those constraints. So this is R1, this is R2. So if we transpose this guy, multiply it with this one, it must be 0. Right? So we can exploit the first constraint. This is my constraint, so they are 0. Everyone happy with this constraint? This constraint just results from the fact that R was a rotation matrix. And I could relate the elements of the homography with the inverse of the calibration matrix, which I don't know at the moment, but I want to gain knowledge about it, and the columns of my rotation matrix. So those guys I know, and I want to know those. So I'm getting closer. The next thing I can exploit is that they both have the same length. So I simply take R transposed, R1 transposed R1 is 1, and it's the same as R2 transposed R2, because they're the same length. Or length 1, the same length. So I can simply, so this is R1 transposed R1 equals R2 transposed R2. What I can do is kind of subtract this element from both sides. So I get this one minus this one equals 0. That's exactly what I've done here. So this one stays the same, and this one over here, the negative part equals 0. Okay, so what I have now is I have two constraints. And what I now want to do is I want to exploit those constraints on estimating my matrix K. Okay? So our goal is now, we have our homography already. We want to estimate my matrix K because this contains the intrinsics, those elements I'm interested in. Yes, please.
K minus T means K minus 1 transform.
Transpose of the inverse. So so this is K to the power of minus T is the transpose of the inverse of K. Okay, so now just to copy paste. Take those two and copy it on the next slide. And I have that in here. I said, okay, in all these equations I have this weird matrix K transpose of the inverse times the inverse. So let's simply define a new matrix B. Say that's B, that's B, that's B. So just simplify that. This is what I want to solve. And that's fine if I do that, because if I want to estimate, if I know B from this matrix, I can actually, through a Cholesky decomposition this time, recover the structure of K. And the reason is, so this matrix, the transpose times itself, is a symmetric positive definite matrix. Even positive definite, not only positive summative definite, because I know the main diagonal of K has values return on 0, so I can directly get that. And I know that this matrix B has 9 elements, but only 6 of them are distinct, because those 3 elements are those elements over here. Right? If I know B, I can compute the Cholesky decomposition. Cholesky decomposition is A transposed, so that A is the inverse, the transpose of the inverse. So then, what I get out of here gives me the transpose of the inverse, so I need to transpose it, invert it, and I get my matrix K. Okay, so what I need to do is I need to determine these parameters, these 6 parameters, from these equations. So take this block, take those equations, and actually solve them. So this is my vector of unknowns. Now I have only 6 elements, not 9 as before, even 12 as before, only 6 elements. And what I can do is I can construct now a system of linear equations in the form V times B equals 0, where I define those V's by using the elements of my homography. and some vector v that I will define in a second. Exploiting the constraints that I have, the first constraint resulting from the orthogonal basis and the second one resulting from the norm 1. So the matrix V is basically two constraints. So the first one was that this guy, okay, so maybe was that too quick? I guess it was a bit too fast. So I had my two constraints. So these are the equations. So this was supposed to be 0 if this had the index 1 and this had the index 2. And this is supposed to be 0, index 1, 1, and index 2, 2. These were the constraints. They resulted from the rotation matrix. Then I was here. I said, okay. And this is a general mapping which resulted from the multiplication of the homography originally. So I said if this was 1 and 2, so if I equals 1 and j equals 2, this must be 0. So v1, 2 times b must be 0. This was the first constraint. This resulted from that they are orthogonal. And then the second one was if I have this element with 1, 1 minus 2, 2 should also be 0. So v1, 1b times v2, 2b should be 0. That was the second constraint. I said, okay, I have two perfect constraints that I now can exploit. And I simply build up a matrix H which says v1, 2 and v1, 1 minus v2, 2, all transposed, times b should be 0. Where v is defined exactly in this way, and this just comes from the multiplication of the homography. So what I have now, I build up, I define this vector v, and with this vector v I can very easily define for a single image those two constraints. So if I have one image, I can do that with multiple images. I can stack n images on top of each other. So in every image, I estimate the homography, and for every image, those values will be different because those consist of the homographies. So I built this up in having two n elements in here because every image contributes those two constraints. Then I have a system of linear equations which I, in the end, can solve and obtain a solution for b. Once I know b, I can recover k. So what is needed? I need to have at least 3 images like this. Of course, the more images, the better it typically gets. And in every of those images, I need to be able to identify at least 4 points. I need these 4 points per plane to compute the matrix H, to compute the homography. So how this plane is mapped onto the image. And each plane gives us 2 equations. These were exactly the equations I had before. As a result of that, as this matrix B has 6 degrees of freedom, 6 elements, I need to have at least 3 views because 3 times 2 equations gives me the 6 degrees of freedom. So I need 4 points per image, 3 images of that type, and then I can solve this system of linear equations which gives me B, and once I have B, I can easily compute K just by Cholesky decomposition. Okay, now exactly the same things happened as before. What I want to solve the system of linear equations as we have again the trivial solution B equals B is 0, which I'm not interested in because this would be a calibration matrix which is 0. I impose the additional constraint of norm 1, and then, so what I'm basically doing, I'm minimizing this equation, which is again the eigenvector problem, very, very similar to what we did in the DLT. So we use the singular value decomposition, take the eigenvector, which corresponds to the smallest singular value or the smallest eigenvalue, and then I obtain the solution for B, which minimizes this expression. That's it. Now we have our calibration matrix, and we're done. With the checkerboard pattern, at least 3 images that can identify all points actually can compute the intrinsic parameters. Of course, in order to get a robust estimate, I should take more images. And I shouldn't see more than 4 points per image. But it's kind of the minimum that I need. Now I can even go a step further and say, okay, now I have all that done. Can we also estimate the nonlinear errors. So last week we talked about nonlinear errors like radial distortion, for example. And they are simply a nonlinear mapping which is added after applying the calibration to the direct linear transform, so the mapping of the direct linear transform. We have the additional other distortion parameters, and if we know them, we can correct, for example, make straight lines straight again, which are mapped as non-straight lines due to the nonlinearities. So there's an example model. I don't want to go into the details. This is basically what we had the radial distortion model, which has the individual parameters, and R is again the distance from the principal point. I don't want to go into all the details. They're you can make those models complex and more complex. We basically do first the projection onto the image and then apply this correction. The key thing is we have some nonlinear parameters in there. And once we have the calibration matrix, we can again apply another standard least squares approach to that and say, okay, what we want to minimize is adjust the parameters of my camera calibration, and I take the ones I computed as my initial values before. I have now these nonlinear parameters and my rotation matrix, and so where the camera is and where the center of projection is. And then I simply say what I want to minimize, wrong font, I'm sorry, this should be homogeneous vector. So it goes over images I and points j. And this is kind of the nonlinear mapping. So where is the estimated, the point expected to be, given I know where it is, given the position of the camera with respect to the world reference frame, the nonlinear parameters and the linear parameters. And then I go with a standard approach, I obtain a quadratic function, I linearize it, I obtain a quadratic function, compute the first derivative, set it to 0, and iterate. And in this way, I typically I refine my calibration matrix K, and I put nonlinear parameters. And the complexity of this function over here simply results from how complex I make this model over here. This is just one example. They could be more complex, they could be easier. This is just kind of the radial distortion or tangential distortion are those kind of standard things to compensate, especially for wide angle lenses. And if I do that, these are kind of the results. So this is my, before calibration, I take my images, and then I can actually correct for that and get my calibrated images out. What we can see over here, for example, that this guy, this line, which is here clearly not a straight line, is a nice straight line over here. Also, we can nicely see that here, that those lines are now also mapped into straight lines. Just an example how this was done for a simple webcam, just holding a webcam in front of the checkerboard. I can estimate the parameters, also the nonlinear ones, through a standard least squares approach after I estimated the linear calibration matrix, so those 5 parameters. So to sum that up, what we have done in the beginning, in the first lecture today, on the first hour today, we looked into the DLT, where we don't use any checkerboard pattern. We just need to know locations of some random points in the scene, which should not lie on a plane. In the second part, we said, okay, now let's simplify this process of estimating where those points are in the real world. Just put everything on a checkerboard, something we can print out on a printer, glue on a flat surface, and hold it in front of the camera. By smartly setting the coordinate system, we could actually simplify those equations and estimate the parameters of the calibration parameters of this camera. The only thing we assumed was the pinhole camera model at the first round. In the second round, we can add nonlinear distortions and estimate the parameters of these nonlinear distortions with a second least squares approach. With this approach, we can actually do camera calibration by just printing out a piece of paper with a checkerboard, gluing it on a flat surface, holding it in front of the camera, estimating the intersection of the red and the white and the black crosses, have those points, and we are done. This is kind of the standard MATLAB calibration toolbox actually works in this way, which you can use to estimate the intrinsics parameters of your camera. That's it basically from my side. What is an outlook for next week? What happens next week is we assume to have this calibration matrix. So we have done this calibration now. I have calibrated my camera. And now I take images of the scene And now I want to estimate where the camera, given I know a few points in the scene. And it turns out we need 3 or 4 points in the scene in order to estimate where the camera is, if we fix the calibration parameters. That's what we are going to do next week. The first part, so the DLT, is Wolfgang's script, one of the best references for, and the Sung, this is the original paper from 1998 on performing this camera calibration, which we have seen in the second part of the course today. Is there any question I can answer? All done. Okay. Yes, please.
Also was zum Webcam neben Sie gesagt haben.
Ja.
Kalibriert man die dann nur ein einziges Mal oder wird die immer wieder irgendwas neu kalibriert?
Okay, so the question was if we once calibrate a camera, if the camera keeps its intrinsics or not. This depends on the quality of the camera. Extremely cheap cameras, this can change. Also, if you have a good camera, you drop it on the ground, you may need to recalibrate that. The more expensive the camera is, typically, or the better also the mechanics and the lenses are in there, the less often you need to recalibrate them. If you have a zoom lens, you actually need to recalibrate it every time because the camera constantly changes if you zoom. But if you have a fixed zoom, if it's a decent camera, you can calibrate it once, unless you expose it to extreme temperature changes, for example. So if you calibrate it at room temperature and go out at minus 20 degrees, just due to the temperature, the parameters of the camera changes. That's something that you can experience in aerial cameras. If you do aerial photography, the cameras are calibrated indoors, let's say at 20 degrees Celsius. Take it in an airplane, fly very high, it can easily go down to whatever, minus 30, minus 40 degrees Celsius, and then the camera parameters change. Therefore, for those applications, we actually need to estimate or re-estimate those parameters very often. Even during a flight, you need to adapt the camera calibration. But if you're, let's say, standard indoor settings and you don't drop your cameras on the ground, the camera is not the most cheapest ever thing with a fixed focus length, you calibrate it once and you're happy with it. Any further questions? If this is not the case, thank you very much for your attention, and the last lecture of this summer term for the photogrammetry course will be next week. Thank you very much.